The last 4 videos have focused exclusively on hydrogen or proton NMR, which is typically the most useful NMR technique. But other useful information can frequently be obtained from carbon NMR. (13C) is only 1% natural abundance. So the technique of carbon NMR is complicated by the fact that 99% of the carbon atoms in the molecule are invisible to the nuclear magnetic resonance spectrometer. And this typically means that we need to run a large number of scans, where a proton NMR we might get a good quality spectrum of 8 scans. The carbon NMR typically takes 200 to 500 scans to obtain an appropriate signal-to-noise ratio. It's very unlikely that there are 2 carbon NMRs next to each other, so we don't have to worry about carbons splitting each other. But since hydrogen exists almost exclusively as the protium isotope, which is NMR active, we do have to worry about the hydrogen splitting the carbon that they're attached to. So in this hypothetical molecule of ethanol, we would see this carbon, and we would not see this carbon. And this carbon would be split by the 3 adjacent hydrogens, and we would expect to see a quartet. 3 adjacent hydrogens that are magnetically equivalent. Would follow the n+1 rule, and we would see 4 peaks, and we would see them with the same 1 to 3 to 3 to 1 ratio that we saw for a hydrogen that was adjacent to a CH3, for example. On average, on a large number of molecules, sometimes this will be carbon-13, sometimes this will be carbon-13, and we would expect for this one, if it were carbon-13, to see a triplet, because there are 2 adjacent hydrogens. And we would also expect to see it further down here. As I mentioned before, carbon NMR typically encompasses a much larger range of parts per million, from 0 to 210, rather than from 0 to 12 or 13. But normally in this range from about 190 to 210 is where we see ketones and aldehydes. Typically somewhere around 170-ish, 170 to 180 is where we see esters and carboxylic acids. COOR and COOH groups, as opposed to RCHO and RCOR. The range for alkenes, carbon-carbon double bonds generally show up between 100 and 160. Typically somewhere between 65 and 95 is where we see the alkynes. And then in this range from about, say, 50 to 90 is where we see ethers and alcohols. directly bound to oxygen. Carbons that are bound to chlorine, bromine, or iodine show up in regions slightly less far downfield, so maybe 40 to 50 for carbon chlorine, 30 to 40 for carbon bromine, 20 to 30 for carbon iodine, something like that. And then in this region from about 5 to 40 is where we see our alkanes. The carbon adjacent to a carbonyl, for instance, a methyl ketone, is around 30 to 35 ppm. And carbons in an allylic position are in approximately the same region, maybe 20 to 50 parts per million, I think, something like that. Maybe not quite as far down as 50. 20 to 40. So it's the same kind of system. You'll look at the far right-hand side for your alkane peaks. You'll look a little further downfield for your things that are adjacent to a pi bond, either CO or a CC pi bond. You'll look a little further downfield for things that are attached to electronegative elements, with the ones attached to oxygen being furthest down. And then you'll look for your alkynes, your alkene and aromatics, and your carbonyls further downfield respectively. So you're kind of looking in the same region, even though the numbers are much bigger. You will also generally see at 77 ppm a 1-to-1-to-1 triplet. Because the solvent we usually use is deuterated chloroform, CdCl3. Deuterium is an NMR active nucleus that has a spin equal to 1 rather than 1/2, which means it has 3 states corresponding to -1, 0, and +1, or alpha, beta, and gamma, if you want to use Greek letters. They're all equally likely, and the deuterium will split the carbon into 3 separate peaks. So we usually see at 77 ppm a solvent peak, which we have to be careful to ignore when we're analyzing the spectrum. So one complicating factor of carbon NMR is caused by the low natural abundance. And what that means is if we allow the hydrogens to split the carbon so that we don't even see a single peak, we see a 1-to-3, 3-to-1 quartet, we'll actually have a very poor signal-to-noise ratio. And that would require even more scans. Sometimes for a very dilute sample, especially if it's high molecular weight compound, it's actually necessary to run these spectra overnight in order to get enough resolution. We can simplify the carbon NMR spectrum by putting all the hydrogens into the beta state. Recall that carbon absorbs, with a 7 Tesla magnet like ours, 785 megahertz radiation, whereas proton absorbs 300 megahertz radiation. So if we apply a broad range of radiation in the 300 megahertz region, we can put all of the hydrogens in the beta state while not affecting the carbons. And then we can use a second radio transmitter to apply 75 megahertz radiation at a wide band and see which of those much narrower focus bands are actually absorbed. This is called band, alternating phase, low power, at peak, for 0 residual splitting. And has the kind of cute acronym Waltz, because we like cute acronyms. And is referred to as Waltz Decoupling. It prevents the splitting of a carbon signal by the attached protons. Sometimes it's just referred to as broadband decoupling. What that means is all 13C signals are sigless. Which greatly simplifies our analysis. But we also don't get the information we would get about the number of hydrogens that are attached to it or what kind of environment those are in. So it's a trade-off. We get a better signal to noise because all of the area is under a single peak rather than split into 4 peaks, so we can run a faster experiment with fewer scans. And we still get essential symmetry information, but we don't get the details. We also introduce another complication, which is that when we're doing broadband or Waltz decoupling, so they're uncoupling hydrogens from the carbons, we can no longer integrate. Because the integration now depends not only on the number of magnetically equivalent hydrogens, or carbons, sorry, that give rise to that signal. But the integration also depends on the number of attached hydrogens. The more hydrogens that are attached, the more intense the peak will be. This is referred to as the nuclear Overhauser enhancement. Which has another cute acronym of NOE. After Herr Overhauser, who's the one that discovered it, and means that if a peak is twice as big as another peak, it might be because there are 2 carbons giving rise to that signal and only one giving rise to the other signal, but it might also be because one of them is a CH3 and the other is only a CH. Methyl groups are more intense than methylene, and methylene peaks are more intense than methine, and quaternary carbons, like a carbonyl group, are very small. Sometimes so small that they're not detected. And that can run into a real problem. One of the members of my research group at the University of Utah cost himself 6 months of research by not running his carbon NMR down far enough, so he missed the carbonyl peak. He thought he had identified a new compound. He spent 6 months synthesizing the compound he thought he had identified, and then when he took a spectrum, it didn't match. And he went back and took a spectrum and found the carbonyl carbon at 215 that he missed the first time, and discovered that it was a well-known compound that several other people in the lab had isolated in the past. So it's a little So we almost always do this Waltz decoupling, which makes our carbon signals more intense, but also introduces the nuclear Overhauser enhancement that prevents us from being able to use integration. But that's kind of good, because now you don't have to worry about doing integration. The most important thing that we get from a carbon NMR is information about the symmetry of the molecule. Typically, we have other ways of determining what the molecular formula is, so we know how many carbons are in the molecule. And if the number of peaks we see in the carbon NMR is not the same as the number of carbons in the molecule, then we know that there must be some symmetry to the molecule. As an example, if you look at 4-bromo-benzaldehyde, versus 2-bromo-benzaldehyde, you would expect to see a different number of carbon signals in the carbon NMR, because for the 4-bromo-benzaldehyde, you've actually got a plane of symmetry that will cause the two carbons in the 2 position to be identical. So you would expect to see, can you do this one? For 4-bromo-benzaldehyde, only 513 C signals. Whereas there's no symmetry here. So you would expect to see 713 C signals. The location of the peaks would not necessarily allow you to tell the difference there, because in both cases you've got an aldehyde which should be at about 210 parts per million, and you've got 6 hydrogens in the benzene ring, which should be in that 100 to 160 range. But in this case, you'll only see 4 peaks in that 100 to 160 range. But in this case, you'll see 6 peaks in that 100 to 160 range. So one of the main things that you use carbon NMR for right away is to look for symmetry in the molecule. And then if you see a peak between 200 and 210, it's a pretty good piece of evidence that it's an aldehyde or a ketone. So additional information about functional groups can be obtained from the carbon NMR as well. Another problem with carbon NMR, of course, is that because we have the nuclear Overhauser enhancement, but we also have the possibility of magnetically equivalent carbons, we can't necessarily tell from the carbon NMR directly whether we're looking at a CH3 group or a CH2 group or a CH group. If we ran proton-coupled carbon NMR spectra, we could, but with proton decoupling, we've lost that piece of information. There's another carbon NMR technique called DEPT, which stands for attached proton test. Another acronym. And the APT spectrum will flip CH2 groups upside down. You need CH and CH3 groups breaking up. And render quaternary carbons invisible. We're putting energy into the proton domain at around 300 megahertz, and we're putting that in such a way as to have it talk to the carbons it gets attached to and tell those carbons how many hydrogens there are attached. It's extremely complicated physics, waiting on the scope of this class or even many graduate spectroscopy classes. But in essence, what it will do, you have free methyl butanol is it will take the two CH2 groups and flip them upside down. So you'd expect to see your triplet at 77 ppm for your deuterated chloroform. Since deuterium absorbs at a different frequency, the proton, even when you're decoupling proton, you're not decoupling from deuterium, so the deuterium will still split the carbon, since it has 3 spin states into a triplet. You will then see a CH2 group upside down at maybe 60 ppm, because it's the carbon attached to the oxygen. You would see another CH2 group upside down at maybe 45 ppm, because it's close to the oxygen but not on the oxygen. And then you would see a peak up, and then another peak up, which would be more intense. This would be the CH group. This would be the CH3 group. And this one will be more intense, both because there are 2 of them, and because with 3 hydrogens you have a bigger ALE. So we see a pattern that looks like that, where we've got 4 magnetically different carbons, 2 of which are upside down because they're CH2 groups, and 2 of which are right side up because they have an odd number of hydrogens attached to them. So the odd number of hydrogens are up, the even number of hydrogens are down. And in the APT, our solvent peak at 77 ppm will actually disappear because there are 0 hydrogens attached. So the regular spectrum will have this peak, and the DEPT or the APT spectrum will no longer have that peak for the CDCl3, which is another way we can recognize that it was a solvent peak because it goes away. There's a slightly more sophisticated technique called distortionless enhancement by polarization transfer. Or DEPT. As the acronym. And distortionless enhancement by polarizing transfer is somewhat similar to the attached proton test. But what it will allow you to do is have separate spectra that show only the CH3 groups, only the CH2 groups, and only the CH groups. So for that same example, we would see our CH3 group with just that one peak. We'd see our CH2 group with our 2 peaks. And then we would see our CH group. And then we see the full spectrum, which would have the triplet for the CDCl3. I didn't get that to scale. See the triplet for the CDCl3, and then we see our CH2 next to that hydroxyl group. So this would allow us to determine that this peak here, the most upfield peak, is the 2 CH3s, this peak here is the CH, and then these 2 peaks here with the CH2. The physics behind why that happens, we won't go into. But effectively what you're doing is you're doing an attached proton test which flips the typically the one that shows up nothing but CHs, right, from the original spectrum. We can get one that shows only the CH3 groups. So you may have the opportunity to run the attached proton test in the second semester course when you're running the NMR, which will help you to identify the number of hydrogens, methylene, methide, methyl CH3, methylene, CH2, and methine is a CH. If there were any quaternary carbons, they would appear only in this whole spectrum and not in any of the other spectra. So carbon NMR is useful for symmetry, and by using some fancy carbon NMR